All right, so this, once again, we're going to figure out the radius of the sun in terms of astronomical units, and there's, of course, the reason that we're doing that is they give us the size of the sun for one astronomical unit, and then 5 astronomical units for part B. All right, so anyhow, it turns out that there's 1.5 times 10 to the 8th kilometers, or 10 to the 8th, sorry, 10 to the 8th kilometers in 1 astronomical unit. So notice the kilometers cancel, and so you take the size of the sun divided by 1.5 times 10 to the 8th, you get a very small number, so it's 0.0046 astronomical units, in order AU. All right, so that allows us to do this problem, because now we can put in the size of the sun for both part A and for part B with using this number right here, 0.0046 AU. All right, so that allows us to solve the problem. All right, so here we go. All right, so don't save. All right, so this is for part A. All right, so for part A of number 3, we get the following: the luminosity for, I'm going to call this the luminosity at 1 AU. 1 AU is going to equal, well, it's since the size of the radius of this thing is 1 AU, so that's going to be 1 divided by, see, this is why we did this conversion, 0.0046. And of course, the AUs cancel, right? This would be 1 AU, and this would be the size of the sun in AU, and then of course the AUs would cancel. Anyhow, you square that, and then you take the temperature of the sun. The temperature of the red giant when it's 1 astronomical unit, and they give us that's 3,000. And we divide by the temperature of the sun, which, we can use, the sun is actually 5,800 Kelvin, but I think for the purposes of this problem, we can just put in 6,000. It makes life a little easier, and then we raise that fraction to the 4th power, right? And then that's times the current luminosity of the sun, right? And so that this is of course how we do this problem, and so this thing is going to be much brighter than the sun, but this is going to give us the fraction, the number of times brighter than the sun that it's going to be. All right, remember, do what's in the parentheses first. Okay, so 1 over 0.0046, you square that, and then you multiply that times 3,000 divided by 6,000, of course, that becomes 0.5, but it's 0.5 raised to the 4th power. All right, so anyhow, when you do that, you get a luminosity of, let's see, what do I have in my calculator here? Roughly 2,900 times the luminosity of our sun. All right, so this is when this red giant would be, 1 astronomical unit. All right, so the luminosity when it's 5 astronomical units, when it's 5 AU. All right, so this is part B. It's the exact same numbers, but now instead of having a 1 right here, you have a 5, right? So it's going to be 5 over 0.0046, which I have saved in my calculator, and we square that. And then you take 3,000, once again, it's the same temperature, divided by roughly the temperature of the surface temperature of our sun is almost 6,000 Kelvin, and then we raise that to the 4th power, and that's going to be times the luminosity of our sun, luminosity of the sun. And so what does that number come out to be? All right, so we're going to figure that out. So this turns out to be 72,503. 503.6 or something like that. Anyhow, we could call it 504. That's perfectly fine, times the luminosity of our sun. So this is when it's, 5 astronomical units, when it's expanded to about the orbit of Jupiter. All right, yeah, notice it's going to be, in the first case, just under 3,000, and then in case B, it's 72,500 roughly. All right, let's do the next problem. All right, so let's see, the next problem, that was number 3. The next problem is number 4. Okay, number 4, let's take a look at it. Number 4, again, we're using the same equation here. Let me just set it up. All right, so the luminosity of now it's going to be a white dwarf divided by the luminosity of the sun. All right, so this is the problem. That's the sun, is equal to the radius of the white dwarf, WD will stand for white dwarf, divided by, of course, the radius of the sun. And we square that, and then the temperature of the white dwarf divided by, of course, the temperature of our sun. All right, and we raise that to the 4th power. Okay, so that's the equation. Here, let's take a look at it. Here's our problem. All right, so this is number 4. Let me raise that up. Use the radius, luminosity, and temperature relationship to calculate the radius of a 12,000 Kelvin, twice the temperature of our sun, and a 0.0004 solar luminosity white dwarf. Okay, so what are we trying to figure out? We're trying to calculate the radius. Okay, so that's the thing that we're looking for, is the radius. All right, let's go back to this problem, and let's see, where's my recorder? All right, so we've got to rearrange this equation and solve for the radius of the white dwarf. Right? Of course, it's the radius of the white dwarf divided by the radius of the sun. And then, of course, we take the square root of everything and multiply both sides by the radius of the sun. So we're going to get in the size of the white dwarf in terms of the size of the sun, as we always do, right? So it's going to be the luminosity of the white dwarf divided by the luminosity of the sun. And of course, since this is squared, we have to take the square root of that. And then it's going to be, so notice this is in the denominator, but it's going, to put it on the other side of the equation, that's going to go to the numerator. So it's going to be the temperature of the sun divided by the temperature of the white dwarf, and then, you're taking the square root of something to the 4th power, right? So the square root of that, of course, is it just becomes squared. So now we can put the numbers in. All right. So let's do that. Let's see. I need a new screen here. There we go. All right. So the radius of the white dwarf is equal to, let's see, how much time do I have? Oh, I got plenty of time. Okay. The radius of the white dwarf is equal to the square root of the luminosity of the white dwarf divided by 1, of course, because the luminosity of the sun is defined as 1. So it's going to be 0.000. Let's see, is that all the zeros? 0004. And then, of course, that's divided by 1. But we don't really need to put that. And then we take the temperature of the temperature of the sun, which is, once again, we're going to use 6,000 divided by the temperature of the white dwarf. Remember, how do we get temperature? We always use, remember, Wien's law, right? So, anyhow, and then, of course, we square that fraction, and then this is going to be times the size of our sun. All right, so this is going to be the size of this white dwarf. All right, so when we put the numbers in, the value that I get is, don't forget, you gotta, do this fraction. Here, let me use the mouse here. Do this fraction first, then square it, and then multiply by the square root of 0.0004. All right, so that turns out to be a very small object indeed. The radius of the white dwarf is equal to 0.005. That's supposed to be a 5. 0.005 times the size of our sun, times the radius of our sun. All right, let's see. I think they ask us a couple of other questions. So you could actually put this in. You could put this in the. If you know the radius of the sun, which of course we do, you could say, well, what's 0.005 times 696,340 kilometers, right? So, since we know that's the size of the sun, this turns out to be 3,481.7 kilometers. So that's the radius of this white dwarf, and of course, just as a sense of size, the radius of the Earth, right? So if we compare this to the radius of the Earth turns out to be, this is Earth, roughly 6,400 kilometers. Right, so this white dwarf, roughly half the size of the Earth. Right, this is a very small object indeed. But notice the temperature of this thing it's incredible. All right, so that is number 4. Let's move on. Let's see, how much time do I have? Okay, so let's move on to the next one. The next one is number 7. All right. All right, so number 7 here, let's take a look at the question. It says, calculate the average density of a red giant core of 0.25 solar masses and a radius of 15,000 kilometers. Compare your answer with the average density of the giant's envelope if it has a 0.5 solar mass and its radius is half an astronomical unit, 0.5 astronomical units, with a core density of the sun. All right, so that is number 7. Let's get back to this thing. All right, so that is. Let's make sure. Are we still recording? All right, so so what problem number 7 is trying to figure out is the density of the white of the sorry, not a white dwarf, of the red giant, Okay, so and they give it. So we want to know what that density is. That's the symbol rho. Remember, density is mass divided by volume. Okay, and of course the volume of any sphere is 4 times pi over 3. 4 pi over 3 times whatever the radius is raised to the 3rd power. All right, we're going to use meters in this problem. We're going to use meters, and the mass we'll use in kilograms because that's what they give it to us in. So that's very nice. All right. So the mass of this red giant, they give us this in the problem, is equal to 0.25 times the mass of the sun, right? And so the mass of the sun, of course, is, so I'm going to multiply this times 2 times 10 to the 30th kilograms. Right, so that'll give us basically, 1/4 of a kilogram is the 1/4 of the mass of the sun is the mass of this red giant. So it turns out to be 5 times 10